Welcome to my YouTube channel. In this video, we are going to learn how to determine the magnetic field at point P as a result of current flowing through this square loop. And the formula to use is this expression below. And this expression is given to us by Biot and Sabat. Now, what you can see in this particular expression is the current I that flows through the conductor. Then dl is just a small elemental change, and by the time we integrate over this small change in L, that will give us the entire contribution of the square loop. Now what we have here is a cross product, because this is a vector quantity cross another vector quantity, and this our r minus r prime is the distance from here to here, the displacement from this entire length. So once we know this and this, then we can go ahead and solve the problem. But to determine this particular expression, first of all, we need to know that this expression, which is coming from here to this point, can also be equal to the expression from here to here, the distance from here to here, upward. Now, instead of us to follow this route to give us this one, which is not known, we can substitute this expression with expressions that are known by following these routes. And to follow these routes, we first of all know that this side is my y-axis, this side is my x-axis, and also this side is my z-axis. Now, for us to move from this point to this point, we notice that the length from here to here is going to be L over 2, because if from here to here is L, that means from here to here will be L over 2. And if from here to here is L over 2, it's in the y direction. We notice that by the time we move in this direction, we are moving in the positive y direction. We also need to take our x along, which is going backward. So our x will take negative axis, then added to what? My z axis. And in so doing, we'll get this expression, which will be seen in the next slide. Then our dl, if you notice, it's along the x-axis. So we can replace this, our dl, with dx in the x component. Now, this is where we have our r minus r prime, which is equal to our x minus x prime, y minus y prime, z minus z prime. That's the full expression. Our dl is equal to dx prime x cap. Remember, we said that this dl will be replaced with dx in the x direction. That's current in the x direction. While our dl, if we are in the y direction, if we are flowing in the y axis, it becomes dy prime y cap, current in the y direction. Since there are 4 segments, the current will flow through. That means this expression will be split into 4 segments. From this diagram, we can see that the square loop has 4 segments. This one, 2, 3, and 4. So if we consider the first segment, which is this point that we're interested in, this is our r, and this is the length along the y-axis. This is the length of the conductor which current is flowing through. Now, instead of us to use this r, we'll replace with another term. Now, take note that our minus x cap is as a result of our x going backward to this point. That's why it's taking x cap. Then for our y, you notice that from here to here is L over 2 y cap. The reason why we didn't use L over 2 here is because this one is not in the paths. Because we need to follow from here to here, down here. This path is not along the route that you must take. So that's why we take ordinary x, which is x minus x cap. But along the y-axis, the length is in the root, so we take L over 2, which is given by this expression. Then z is also along the root, so we take z cap. Then we rewrite this one in this form by 3 over 2. Remember that our dl is the x cap. So this one is for the first segment. If it also notice that the limit is from minus L over 2 to L over 2. So for the second segment, we notice that it's along this side. This is my x-axis and this is my y-axis. When you consider this part, if we move from this point to this point, what we notice is that For us to move from this point to this point, we can also go through this length. From here to here is in the roots, that we want to follow. From here to here is also in the roots. But the y is off the roots. So we take our y backward, which is negative y cap. Then for our x, if we move, we are moving backward. So it will take minus L over 2 because this side is also inside the what? The roots that we are following, x cap. Then our z, we have this particular one. So we have this one as our for second segment. For the third segment, you can follow the same approach and you get this expression. For our fourth segment, this is what we have given as this expression. Then we had the fourth segment, but because of the symmetry of the four integrals, we assume that they are all the same. Then we have that our HR, which is equal to 4 times z dot of the entire integral. So it's like saying 4 times the four integral since they are symmetric. So, but we add this z because all of them are pointing in the z direction, and we use dots because they are all vector quantities. So the next thing is for us to take the cross product of the previous slide, our x, y, and z. For the x, you have only the x prime, 0, 0, x, L over 2, and z. By the time you solve this one, this is what you get. You get this expression, and we substitute it into this place because this side is 0. So we have only these two components that are substituted here. So at the end of the day, our I is a constant, 4 pi is a constant. So we'll bring our 4 and 4 pi as expression constants here. We have our integral of dx and this. But if z dots this particular y and z dots this particular one, this is the only expression that will remain. Z dot y will give me 0. Z dot z will give me 1. So this part will vanish, and this is the only expression that will remain. So which is the x prime, L over 2, then this expression. So the next thing is we have our h equal to this expression. Then for us to solve this integral, we let p squared equal to this expression. That's this and this. P squared equal to this expression. Then we can now say let x prime equal to p tan theta, where dx prime is equal to p sec squared theta d theta. If we substitute this into this expression, then this is what we'll get. For the x prime, we have p sec squared theta d theta. For this expression, we notice that if you replace this p prime, it becomes p tan squared theta, which is this. Then this plus this will give us p squared, 3 over 2. So at the end of the day, we have p sec squared theta d theta. If you factorize your p squared out, you have tan squared theta plus 1. Now, tan squared theta plus 1 is the same thing as sec squared theta. But take note that the sec squared theta that will come in from here is raised to power 3 over 2. The 2 will cancel the squared, and you have sec cube theta. Then p squared that is here, we multiply this. 2 will cancel 2, leaving p cube here. Then you now have this expression, which will result to this, because p will cancel p, one of the p here, leaving p squared. Sec squared will cancel sec, but remember, one of the sec that is left here, 1 over sec is 1 over cos theta, and cos theta will go up, which is this, then d theta. So at the end of the day, we bring out p squared because it's not a function of theta. We'll have this expression, then integral of cos theta. So if we integrate cos theta, we have sin theta from our limits. But remember, we said our x prime is equal to p tan theta, which is the same thing as x prime over p equal to tan theta. When we draw the triangle connecting these expressions, we have this triangle here, where if this theta is here, then we should know that tan theta is opposite all of our adjacents. So opposite will be our x, the adjacent will be p. So this side, the length of this side will be this given by this expression in terms of x prime and this. Therefore, what will be our sin theta? Our sin theta will be opposite all over hypotenuse, which is given by this expression. So now that we have sine theta here, we can bring this expression into these parts, which will be given by this. Then we can now put our limit L over 2 minus L over 2. At the end of the day, substitute wherever you see your x prime, put L over 2, and this is what we have. And this. Now, this plus came into being because this one, when you substitute this into this, it will now be this minus L over 2 all over this, which changes to plus. So they have the same denominator. L over 2 plus L over 2 will give us L. And our final expression is in the next slide, which is given by this expression. So we now have L over 2 squared, Z squared. So I've already substituted back my P squared into this expression. Now we have L squared, which is this, 2 pi multiplied by, remember our P squared is Z squared, L over 2 all squared, square root of this expression. If you add this plus this, it will give us L squared over 2. Because this one is L squared over 4, L squared over 4. L squared over 4 plus L squared over 4 will give us L squared over 2 plus Z squared. Now that we have this expression, we can bring it down in this form, which is given by this. So we can end here as our final expression for H. Or you can say factorize L squared out from this expression. L squared out. If you factorize L squared out, it will be Z squared all over L squared plus 1 over 4. That L squared that will be out here, we cancel this L squared. So you can have it in this form or this form. I hope this video helps.